This is the homework help for the light wave math problems. You've got your equations up here at the top. You have speed of light equals wavelength times frequency, and speed of light equals distance over time. The c is the same as the v in our other wave formulas. We're just talking specifically about speed of light instead of speed of waves in general. The speed of light in a vacuum is considered 3 times 10 to the 8th meters per second. That is a given number. It's on your formula sheet. Light does slow down when it leaves a vacuum, so when it enters air, slows down just slightly, even slower in liquids and even slower in solids, so that's something to keep in mind. Okay, if we take a look at number 1, it's really just a conversion problem. You're converting into micrometers, which is the little Greek letter here, this one, and then nanometers. Those are two very common units that you're going to see in this unit. And if you notice, they tell you that a micrometer is equivalent to a millionth of a meter, or times 10 to the negative 6th, and a nanometer is times 10 to the negative 9th, or a billionth of a meter. Okay, so really, really tiny numbers here. Okay, so red light from a helium neon laser is 0.000000633 meters. So very, very tiny wavelength. They want us to convert it into micrometers and then into nanometers. So the easiest way to do this in this particular one for micrometers is just to count over 6 places. So we've got 1, 2, 3, 4, 5, 6, and we see that we have 0.633 micrometers. And then for nanometers, we want to count over 9 places. So if we go with our 6 here, and then 7, 8, 9, that gives us 633 nanometers. Now, something important to remember is in the problems, most of the time they're going to give you the wavelength in nanometers or micrometers, and you're going to have to convert it to meters. So the way to do that is to say 633 times 10 to the negative 9th meters, or 0.633 times 10 to the minus 6th meters, depending on which unit you're given. So again, you're just taking the exponent that's listed in the factors column on your conversion sheet, you're tacking it on the original number, and that's converting. Let's take a look at number 2. It asks us to calculate the frequencies for these 4 colors of light. So letter A gives us violet light, tells us it is 400 nanometers. So that's going to be a wavelength, which is the lambda symbol. We want to go ahead and convert nanometers to meters. So remember, nano is times 10 to the negative 9th. So we're going to keep 400 exactly the same. We don't mess with where the decimal is or anything like that. We just tack on times 10 to the negative 9th, and that is converting. We also know that violet light is going at the speed of light, so C is 3 times 10 to the 8th. This was not given in the problem, but it is assumed that you know it. Remember, we had that up here at the top. And then the question is, what is the frequency? So our formula that would make the most sense to use is C equals wavelength times frequency, and you're trying to solve here for the frequency. The last one I want to look at is number 5, which is on the top of the page on the back. Tells us that Mars is approximately 90 million kilometers from the Earth, and we want to know how long it would take for radio waves going from a camera mounted on the Mars rover to get to Earth and back. Okay, so first they give us a distance. 90 million is 90 and then 6 zeros added to that. And then we have to remember it's also in kilometers, and we want meters. So kilo is times 10 to the 3rd. So you could go ahead and write 90 million times 10 to the 3rd, or you could add 3 zeros, or just to save on space, You could count over, starting from the back, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and say 9 times 10 to the 10th meters. Any of those options will work. Secondly, we know that radio waves are light waves, and so the speed of light is another given. And again, it's not stated in the problem, it's assumed that you know that radio is light. And since we're traveling through outer space, the speed of light in a vacuum is 3 times 10 to the 8th. We're looking for a time. How long is it going to take for the waves to travel that far at that speed? And so the formula for that would make the most sense for this one is the C equals D over T formula, where you are solving for the T. Hope that helps. Please reach out as always if you have questions.